Okay, before we continue our study of cyclic and mirrored structures, I wanted to do a quick review of some things from our last class period. So here on the left of the screen, you'll see the Klein Four-Group and the list of CMA structures of order 4. Okay, so I'll leave this up for reference as we do this quick review. Recall that our shuffling demonstrations at the end of our last class video utilize the fact that the Klein Four-Group holds fixed the 3 CMA structure types SOO, OSO, and OOS. Moreover, these CMA structures are simply the orbits of certain CMA sequences. And so here I've written essentially a summary of what we see in our chart on the left. Okay, so maybe just to quickly remind people, SOO refers to the CMA structure where the sequence involved is a 2-cycle relative to same value. It is mirrored relative to opposite value, and it is an AMP relative to opposite value. So here you can see that each one of these satisfies those 3 conditions for an SOO structure. And off to the right, I indicate that this set of CMA sequences is actually the orbit of each of those sequences individually. And then it's a similar situation for these other CMA structure types. Now, for our purposes, the stabilizer of an individual CMA sequence will be of limited value, since it merely tells us which members of the Klein Four-Group fix that particular CMA sequence. As we can see here, this tells us only that the 50% cut fixes the CMA sequence 1010. But as we saw last class period, we are far more interested in knowing which members of the Klein Four-Group either fix a given CMA sequence or convert it to its complement, where zeros and ones switch places. And as just noted, the orbit of a CMA sequence precisely consists of itself and its complement, which are the pairs of sequences we are actually interested in. Therefore, even though the stabilizer of an individual CMA sequence may not be of great interest or importance to us in the study of cyclic and mirrored structures, the notion of the stabilizer of the orbit of a CMA sequence will be of paramount importance. Notationally, we can represent this by the stabilizer of the orbit of X. For instance, applying this to the CMA sequence 1010, we would write the stabilizer of the orbit of 1010. This stabilizer subgroup ends up being the entire Klein Four-Group. Okay? So as a final point of clarification of notation, consider the label SOO. Now we know that this refers to the characteristic of a CMA sequence that has structure type SOO. It can also refer to the actual set of CMA sequences having that particular structure type. Okay? So consequently, we may say that 1010 is an SOO sequence. That's a perfectly fine way to describe it. But when we write the stabilizer of SOO is equal to the Klein Four-Group, we are viewing SOO as a set, namely this set of CMA sequences, each of which has an SSO structure type. Okay, so provided that our chosen group G is abelian and is acting on our set of CMA sequences in a way that the CMA structure types coincide with the orbits of X, we can employ the stabilizer notation as used above. Okay, well, that's enough of a review there. Okay, now, during our next class video, we will explore a generalization of the Klein Four-Group to a group of order 8, and from there to a group of order 16. So I thought we would just bring up quickly what we will be looking at. So here on the left, you'll see the Klein 8 group, call it V8. Often the Klein Four-Group is referred to as V4. So I've generalized it. To my knowledge, I don't know if anyone has generalized the Klein Four-Group in the way that I am generalizing it here. It's a very natural way of doing it. And it takes advantage of the same 3 shuffles that we were using for the Klein Four-Group. But now we have 8 cards. And then we'll move from 8 to 16. You can go to 32 and so forth. Anyway, that's kind of where we're headed. So I thought we would just give you a quick preview of the Klein 8 group and how we will be using it. So really what I have here is just a summary of information on the chart to the left there. If you recall these angle brackets here, it's telling us that whatever elements are in here, they will, quote, generate the entire group. And so what a person would need to do is we're going to use these as generators. And so what would happen is we would need to find all, quote, products of these 3 with themselves. So we would have to find the square of this one. We apply it twice, same thing here, same thing here. Well, we can see what's going to happen with the squares. All of these are of order 2 individually. And then we would have to take all combinations and all orders of these, right, and multiply them. And we'll find that we actually get 8 elements. And we can see that if I'll use the mouse here. Here's a list of all 8 permutations that make up the permutation representation of the Klein 8 group. And it ends up being, which is very nice, isomorphic to the direct sum of Z2 with itself 3 times. And of course here I've just noted that the order of it is 8, okay? So that's a very nice group to work with, as we'll see. So here's a demonstration of the Klein 8 group in action. So here are some important properties of the Klein 8 group. The first one is, as I mentioned, V8 is generated by 3 elements, each of order 2. V8 is abelian, since it's isomorphic to direct sum of Z2 with Z2 with Z2. And then our third important property is that any combination of an even number of each of the shuffles TCR in any order returns a packet of 8 cards to its original order. Okay, so that's a lot to digest. Okay, so we'll look at it in detail here. So, and then the fourth property that we'll take advantage of is that a single application of each of the 3 shuffles, TCR, so the transpose, 50% cut, and the packet reversal, in any order will yield this permutation. Okay, so what this is saying is this is different than what we saw for the Klein Four-Group. If you remember, The important property of the Klein Four-Group was that if you performed a composition of all three of the non-identity elements in the Klein Four-Group, you would always get the identity. So all of these, if we were in the Klein Four-Group still, these would all be the identity permutation, okay, or the identity shuffle in our case. Okay, well, that's no longer the case. We're now in a group of order 8. Okay, so the group generated by those same or analogous generators that we used for the Klein Four-Group, it's going to give us a different group with certain properties that differ, right? So what is being said here, we'll refer to it a little bit later, but is that if you take any order of T, C, and R, you'll get this permutation. Okay, well, what does that mean? That means if we start with the ordered packet ace of hearts, 2 of hearts to 8 of hearts, after applying the above permutation, the new ordering will be always, always, always 3, 4, 1 or ace, 2, 7, 8, 5, 6. So I have a note here. If you are willing to memorize this sequence, which isn't too hard to do, 3, 4, 1, 2, 7, 8, 5, 6, it's kind of like memorizing a phone number. You can do some amazing things. Okay, so I'll remind you of that. Now, with what we're doing here, you have to realize that this is a kind of a preview here. Now, what you'll see here is looking very similar to that first demonstration that we did at the end of the last class video, the one in which we allowed them to choose what order we mix these things, okay? So we're going to do the same thing now, but with a packet of 8 cards. Far more interesting. We have 8 cards now instead of just 4. So we've kind of reviewed that first demonstration with what I just finished there. So let's start with an ordered packet so we can kind of see what's going on. And then I'm really hoping that people have watched that previous class video because it will help make sense of what we're doing here because we're really just repeating the same thing, but now with 8 cards. But also, it's going to be more powerful. In fact, the surprisal level for this is through the roof, as you'll see, because we have 8 cards instead of 4. Okay, so if you recall, what we did was we're going to do this 4 times. That's what we did last time as well. At this point, pretend I am speaking to you as the spectator and, explain to them that you have this very interesting demonstration that you want them to see involving free choices, okay? And what we find is some people are able to just intuitively make choices that lead to wonderful outcomes, okay? Whereas the rest of us probably have to work at it and maybe make mistakes along the way. So what we're going to do is I'm going to give you a whole bunch of free choices. And those choices will involve applying different shuffles to this packet of cards. And as you can see, they're in order right now, ace through 8. Okay, so let me just show you what the shuffles are first so that you know what you're choosing. The first one's called a pairwise transpose, okay, and I just abbreviated it T. So you watch me carefully. It's important that I do these correctly, otherwise I could ruin the outcome for you when you go to make your choices. Okay, so the transpose will always, always be done this way. You take the cards and you put down 1, 2, 1, 2, 1, 2, 1, 2. And then you just stack from left to right, just like you read a book from left to right. Okay, so that's the first one. A C, it represents something called the Charlier shuffle, or more precisely, the Charlier 1 shuffle. Okay, so this is where I just push off the top card, bottom goes on top, top goes on bottom, bottom goes on top, top to bottom, bottom to top, top to bottom. You just repeat that until you've moved all of the cards from one hand to the other. And then the last one is, I call it the first shall be last, and the last shall be first. Okay? So what I do is I start dealing out the cards, and ordinarily I would do it until you say stop or something, and then maybe I deal out, two more, and then deal out the rest. Okay, so the first shall be last, and the last shall be first. So this was the last one. So here now we just stack them in opposite order. Okay, great. So that's an example of each of these shuffles. Okay, did you get those down? Oh, you want to see them again? Okay. Well, why don't we do a different order then, if you like? Okay, so the first shall be last and the last shall be first was a little confusing. Okay, in fact, let's go ahead and just give you the chance to tell me when to stop. Stop already? Okay. Okay, great. Okay, and so we take the last one and then we stack it on all of the previous ones until we get to the first. Which one would you like next? We're still just demonstrating these, I guess. Oh, transpose? Okay, so when you get to this point, this is what you'll be choosing. And then we pointed out for it to be done properly, you stack them from left to right, just like you read a book. And then this one's called the Charlier one. So you can watch me that I'm faithfully performing the same actions every time. There's just no shenanigans going on. Okay, well, great. So you've seen each of the shuffles twice now. So I think you have an idea as to what you're choosing. So let me just set these aside here. And now we're going to give you the chance to dictate how you would like these mixed. So we're simply going to do 4 rounds. Hopefully 4 is not too many for you. 4 rounds, and you can tell me what order you want these performed. So which one would you like first? That one? Okay, you quite like the Charlier, kind of a messy looking thing. What next? First shall be last, the last shall be first. Okay, reversal one we often call it too. Of course, by elimination, that would mean that we do that one third. What about the next round? You just want them in the order they're listed here? You sure? Okay. What about the third round? You want 2, what? You want 2 there. Kind of confusing me here with all these numbers. Okay, where do you want, which one first? That one? Okay, and then of course the 3 would have to go there. Just one more. Okay, which one first? That one again? Okay, and then second? Want that one? Right, and then of course third would be right there. Hopefully I haven't influenced you. I think we just had you choose them freely. I don't think I've suggested that you should go with any one order. I mean, this one's kind of curious here. It's in the order listed. Oh yeah, this one's reversed to that one. I don't know if that means anything. But would you like to change any of these? So, oh, you do want to change. Okay, so which one? The last one. Okay, so you're bothered by the fact that that's actually the reversal of this, I guess, or something. Okay, so what would you like for 1 instead? Charlier, okay. And then you want to switch around. You want 3 over here, and then you want that as 2. Okay, so that's great. So now it'll become 2, 1, 3. Okay, so you're happy with that? We'll kind of lock that in as your final choice for mixing these. Okay, well, great. Well, let's just quickly go through and let's see, where your choices lead us. Okay. Now, if you made some good choices, some great things are going to happen. Now, you might wonder what's a great thing to happen, but we'll have to just wait and see. That's the fun of making good choices. Sometimes you don't even know the wonderful outcomes that occur because you've made a good or right choice. Okay, so here, Charlier 1 first. Whoop, I'm sorry about that. So Charlier 1 first. Okay, I'll try to keep it in camera for you guys. Maybe I'll just move that up. Okay, first shall be last, the last shall be first. Okay, I'm going to start dealing these out from left to right as demonstrated at the beginning. And you can tell me when to stop. Stop. Okay. just that one. Okay. Okay, and then these two. Okay. And then the first shall be last, the last shall be first. So the last one gets stacked, and we just stack in that manner. Okay, where are we? Oh, transpose. Okay, so you keep an eye on me. We stack these like we read a book, left to right. That's great. Try not to drop them. This one here. Oh, we do that one. Okay. Okay. Okay, as we read a book. That's very, very good. Okay. Oh, let's stay on track here. So Charlier. Let's call the Charlier 1. And then, okay, you tell me when to stop. Stop. Okay. You want one more? Okay. Okay. And then we just stack the last one all the way to the first one. Okay, we've done that one. Number 1. So we need to do we need to repeat this one here, right? So, oh, yeah, the versal. You tell me, you want to tell me to stop sometime? Okay, that's all you want. Okay, that's fine. Right, okay. And then here we're at a transpose. Okay. Okay, and then we're reading a book here. And then the last one's the Charlier. This one's just kind of a hard one to not just make a mess of it. And then the last one, this is where you actually made some changes, right? You changed your mind a little bit there. Oh, we do a Charlier 1 again. Okay. And then we do a transpose. And then stack, like we read a book. And then the last one is a first shall be last, and the last shall be first. Okay, so I'll start. Okay, you need to tell me, remember, you tell me when to stop. Let's start over here. Well, stop, okay. You want to stop? Okay, great, so we can do that. Okay, it's just stack. Last one goes on top all the way to the left to the first one. Okay, great. Well, let's just see where your choices have led us. Okay, and it's really important to realize that that these were free choices here, right? I mean, we allowed you to decide on the order in which these shuffles are performed. Okay, and we repeated it 4 times. In fact, you even changed your mind here, which is kind of interesting because, let's just think about this. If you had not changed your mind, we would have done the following. We would have done this one first, then a Charlier 1, and then we would have done a transpose last. Okay? So that's how it would have been done if you hadn't changed your mind. But you decided to go with a Charlier 1 first, then a transpose, and then this first shall be last one. Okay? So let's just see what all of those choices have come to, and is there evidence that you are a good choice maker? Okay, well, let's just see here. Okay, well, that's interesting. The ace. Yeah, that's true. We did start with an ace on top, so that's kind of nice. 2, 3, 4. You've got to be kidding me. 5. No way. 6, 7, 8. How did you do that? How could you have made all of these free choices? In fact, you were given a set of 4 of them. We could have done more, but it was a lot of mixing. And you even changed your mind. And boy, are we glad you changed your mind, right? So with all of the choices that you made and the correction to one of the choices you made, you were able to return the packet to its original order. How amazing are you? Okay, so that is the first demonstration. Now, the other ones we'll kind of talk through because they don't necessarily have to be, because they're variations on what we've just done, but they're powerful variations nonetheless. Okay, so demonstration 2 is the same as demonstration 1, except here you allow an odd number of sets, okay? So if you recall, I had some important properties of the Klein the Klein 8 group that I mentioned. Maybe I'll just bring these back up for a second here. So here are some important properties that we'll see and we can verify in the coming class period or two. Let's see. Oh, right here. So any combination of any even number of each of the shuffles TCR in any order returns the packet of 8 cards to its original order. Wow. Okay. So is that not what we did? Okay, so let's go back here for a second and just think about the mathematics involved here, right? Think about the mathematics. Okay, so now each of these is of order 2. You perform any one of these shuffles in isolation, you do it twice, you return that packet of 8 cards to its original order, guaranteed. And it's because you can see off here, I've mentioned it already, but once again on the left here, each of these permutations that correspond to these 3 shuffles has order 2. Okay, so you perform the pairwise transpose twice, you get back to the original order, the same thing for the others. Okay, now another extremely important property that we took advantage of is the fact that V8 is abelian. It's an abelian group. Okay, so it doesn't matter in what order you apply these permutations. So if you do a pairwise transpose and then a 50% cut, it's the same thing as doing a 50% cut and a pairwise transpose. And you may want to convince yourself of that by just, trying those out. It doesn't matter what order you perform these permutations, okay? And that's a property of an abelian group. The operation here is commutative, similar to the property of addition of, let's say, the integers. 5 plus 2 is the same thing as 2 plus 5. It doesn't matter what order you add those. Well, that same commutative property is enjoyed by the group V8. And when it is a commutative group, we say it's an abelian group, okay? So, well, how does that help us? How can we use these two ideas together to explain why it is that all of this mixing would be the same thing as the identity? This is all the identity. Boy, it's a very complicated way of writing the identity, isn't it? Well, why is that? Well, let's just think about this. And many of you probably can see already, but we can go ahead and just write these out, I guess. So why don't we say, now we won't worry about the left to right or right to left, what order we should display these to be true to what we've done here. So I'm going to just list them in the order that we perform them. Okay, so the first thing we did a Charlie A1, and then we did technically a packet reversal. We sold it as this first shall be last and the last shall be first motif, which works. One thing I thought of kind of after the fact is if we're going to use, and I recommend that you use that first shall be last and the last shall be first, it's so much more powerful than just reversing the cards openly, right? Um, maybe what I should have done is give this a different name, right? Right now, R doesn't make much sense if we're going to say first shall be last and the last shall be first. So that was kind of an oversight on my part. So you could call this FL, first shall be last, or some kind of abbreviation that makes sense there. So here's a transpose, Charlier or Charlier 1, and then you can give this a more meaningful name for the sake of the spectator if you would like. But in terms of what we're doing here, it's nice to just have one letter to represent these. Okay, so that's the first round. I'm just going from left to right here. And then we did now on the second, right? So, if I'm making a mistake, you can correct those on your own after, or pause the video and fix them. Okay, so you get that. Whoops, I'm sorry. That's a T right there. And then a C. And then R, T, and a C. Just one more now. Another C, a T, and an R. Now, if I made a mistake, it will depend on the nature of the mistake as to whether this is going to mess us up. So I just need an even number of T's, an even number of C's, and an even number of R's. That's all I need. Okay, so we know that the group is commutative. It's an abelian group. Well, what does that mean with this string of composition or multiplication, if you want to call it that? Well, it means we can reorder these however we like. It won't change the outcome. So if we want to focus on the T's, since we have T, C, R, how many T's do we have? Well, we're not going to be terribly surprised that we have 1, 2, 3, 4. Oh, shoot. Heaven above. Okay, where's the mistake, everyone? Okay, this is the danger in writing and talking at the same time. It looks like I don't know what I did here. I think it looks like I wrote down one of them twice. Okay, so a lot of you, now this isn't, we've already done the demonstration, right? It succeeded. I'm just trying to explain why it succeeded. So I would guess I messed up right here. And you guys probably saw that in real time. It's the third one. The third one, we did R first, then T, then C. Now this one is gone. It's only supposed to be there. Okay? And then this is correct. C, T, R. Okay, great. Okay. We are only supposed to get 4 T's. I mean, that's a consequence of actually how we're playing the game, right? So this is going to be T to the fourth, C to the fourth, R to the fourth. Okay? So there's going to be 4 of each of those. Well, from what I said, I guess you could do this a couple of ways. Now, knowing that, so note, now we've mentioned this 2 or 3 times now, but each of these permutations is of order 2. So this is equal to the identity, or sometimes we just write it parentheses 1. Okay. So, depending on your comfort level with the basics of abstract algebra, you would be able, most likely, many of you could look at this and go, oh, that's just the identity, which it is. Now, if it's helpful for people, and maybe I should have done it this way from the start, so I apologize for that, but there's a lot of ways to kind of get to the end result here, a lot of correct ways of doing that. Okay, well, we can do this, and maybe I should have. So a t squared squared is t to the fourth. So really, this is just inside the parentheses, the identity, and then we still have a square on the outside and so forth. Well, the identity applied to itself any number of times is just the identity. So I think you should find it at least moderately surprising that performing all of these as dictated by the spectator. Now, once again, you could have this come by way of a random process. I mentioned that, right, last time. So if you had a six-sided die, you could have 1 and 2 indicate that you should do a transpose. And then on the die, you could have 3 and 4 indicate you should do a Charlier 1. And then 5 and 6, you would just tell the spectator, if we get that one of those, we'll do this funny first shall be last, last shall be first. Okay, so you could use a die where it's out of the control of both you and the spectator. Okay, so for this to work, what I needed is I just needed to make sure if I'm wanting the identity here, which in this particular case, that was the goal, that was the reason it worked out the way it did, is I just needed to make sure that we applied an even number of each of these individual shuffles. Okay, so if you were a genius, I suppose if you wrote these down, you can keep track, but if the spectator were to just call out shuffles, if you had a mental way or on a piece of paper, a way of just keeping track of, okay, how many transposes have I done? and then maybe gerrymander it so that, eventually you do an even number of them. And the same thing for the Charlier 1 and this packet reversal. First shall be last, the last shall be first. So I just thought, given what we did last time, this is a beautiful extension of what we did with the Klein Four-Group. I mean, it's just like wonderful, because in the case of the Klein Four-Group, anytime you do that, any one of these, let's be careful, not just that one, any one of these, you get the identity, right? Because the product of the 3 non-identity elements in the Klein Four-Group always gives you the identity. So what's nice about that particular property is we could do this any number of times, an even or an odd. Now we just happen to do an even because I think 4 times is enough, actually. But we could have done it a 5th time, and we would have still finished, right, with the same result, same reveal, okay? But to use the property that I'm looking at here, I needed to kind of manufacture a credible way to make sure that we performed an even number of each of these shuffles individually. And this was a nice way to do it, okay? Now, what would you do if you happened to do it an odd number? Okay, and then maybe before we go, think about that, if you don't mind. Think about that. What would you do if the spectator said, can we do one more round? Okay, well, you should be prepared for things like that because they do happen. Okay, well, just think about that. Just kind of mull over that while I try to give you more information, different information. When I demonstrated, and this is important actually, when I demonstrated the original shuffles, doing that for the Klein Four-Group, going through them just once would not pose a problem because, as I mentioned, each line here, each ordering of these shuffles would always come out to be the identity. That's not true here. I have to do an even number of them. Well, if you remember, I did. Because what I did was I went through and I showed each of these. I did it under the guise of, well, we're going to have you choose these shuffles. To really be in a position to make a choice, you have to know what you're choosing. So I demonstrated them once, and then I said, well, just to make sure that you're clear on which one's which, let's just show each of the shuffles one more time. And then I even did a different order, and you'll see that if you go back. Well, I did 2 rounds, and that's even. So I essentially performed 2 transposes, 2Charliers, and 2 of these reversals. So that took it right back to 1 ace through 8. Okay. So anyway, that's important. You don't want to just do it once. Okay. Otherwise, well, if you do it once, this is what will happen. The same thing as what we're going to now explain for an odd number, right? Because if you do it once at the beginning and then an even number from then on, then of course the total number that you've performed those would be an odd number, right? So tying it into demonstration 1, where we made sure that we did it an even number, what would happen, or what would you do if you were asked to do it an odd number? Well, this goes back to something I recommended right at the very beginning. Okay, so let's just mention this again. Now, you'll know why I mentioned it. I mentioned here that a single application of each of the 3 shuffles in any order, I give some examples, yields the permutation this. Okay, and that's the case. So in other words, if we were to start with an ordered packet, ace through 8, after applying the above permutations in that order, in any order, the new ordering of this packet would be 3, 4, 1, 2, 7, 8, 5, 6. Okay, and that just came from applying this permutation to this sequence. Okay, so I'll just show one of them here. So for example, we know that this permutation, so if you were to perform each shuffle exactly once in any order, what it would do is 1 would be sent to 3. Well, what that means then is what was in position 1, which is right here, is going to be replaced by what is currently in position 3. So all that means is where we had the ace of hearts, we now have the 3 of hearts. Okay, and then it's the same thing for all of these other ones. So if you apply each of those shuffles in any order to this packet, you will get this, guaranteed. Well, if you've, just took a few minutes and memorized this sequence, or, I think something even better is to have written down, because, it'll save your brain, write down, before you even talk to the spectator, just write down on a piece of paper this, and, fold it, have it off somewhere out of sight, and you may or may not use it, okay? So when would you use it? Well, you would use it if the spectator, for whatever reason, wanted you to do it an odd number of times. If they want you to do it an odd number of times, you'd say, oh, okay, those are very interesting choices that you made. Oh yeah, I just remembered. I wrote a prediction before we even started any of this. See, it's over here. It's a piece of paper that's folded up. And so you would open up the paper and show an ordering of the cards. And then you would reveal that, in fact, the final order of the cards after an odd number of applications of each one of these shuffles, that it matches your prediction. that was written before all of the decisions, the free choices were made. Okay? Now, if they decide they want an even number, you don't even bring up the fact that you have this piece of paper over here, maybe hiding, with that information on it. You would just do what I did, namely, show that you have returned that packet to its original order. Okay, and so it will have a very similar punch in terms of the response by the spectator. Okay, so that is all that I'm saying here. Do an even number of times, original order, odd number of times, you'll get that. Okay. Really quickly, these are very short here. You could ask for 8 random cards. So really, you could ask for 8 random cards. Say, give me 8 cards, maybe lay them out. And here you could say, okay, are you happy with the order of the cards? And maybe they'll rearrange them or something. And then at that point, you just get out a piece of paper. And so you just get a piece of paper and say, okay, and you don't have to show them what you're writing. Say, I'm just writing down, which is actually true. I'm just writing down the identities of the cards. That's all I'm doing. Fold that up, set it aside somewhere. And then you just go through the same thing that we've just done. Here you'd want to do it an even number of times, which is perfectly easy to justify. Just say, well, 4 rounds should be enough. Then you will return it to its original order. And that order you've written down on this piece of paper. Okay? So that would be a way to do it with a random set of 8 cards chosen by the spectator and ordered by the spectator. Okay? Okay, and then quickly, demonstration 4 is similar to 3, but what you could do here, if you want to bring it up just 1 notch, I guess. So here it's a random set of 8 cards again, okay? But what you could do differently with your piece of paper, you have the cards out, spectators happy with the cards and their order. You say, okay, I'm just going to write down the identities of the cards, which is still actually true. But what you're going to do now is you're going to write them in reverse order to what you see here. So you write them in the reverse order to what they are on the table. Well, why are we doing that? Well, you'll see. So you just write them down in reverse order. And with this one here, where we wrote them down in order, I mean, that's a great, presentation, a way to do it. I don't know if it'll take away from the surprise a little bit, seeing that they may remember roughly that the order in which you wrote them down is actually true to the actual order. I don't know if that would raise suspicions or not, but I suspect that would still be very, very powerful. But here you avoid that entirely because you're going to write them down in the opposite order. They're not going to remember the opposite order of those cards. And well, how do you make it work? Well, you go through the same thing as before. You have them do it an even number of times. So you go through and have them do it an even number of times, same as the demonstration 1. But after you've done that, you can just say, okay, well, boy, you've made a lot of choices. Okay, I just feel like I should give you just one last chance to make an important choice. And think about this choice. It's going to decide the success or failure of what's coming. Okay, so really concentrate when you make this final choice. And so you just do a, quote, packet reversal. You do a first shall be last, last shall be first. And that one, you're giving them lots of choices. You're saying, okay, I'll get off the cards until you tell me to stop. Okay, and so forth. And then you say first shall be last, last shall be first, and stack them. And say, okay, wow, after all of those choices from earlier, and now I gave you a chance to make one final set of choices, What do you think the chances are that the card names that I wrote down would actually be listed in the order in which you've mixed these cards? And they're going to look at you like, there's no way. They did 4 sets of mixing sequences there. And then on top of that, you even gave them one more chance to influence the process by doing a first shall be last, a last shall be first. There is no way that you, as the performer, so I'm playing the part of the spectator, that you as the performer could possibly have written down the final correct ordering of these cards. There is no way you've done that. Well, you will have, right? Because a packet reversal reverses the cards. I mean, we can see that here. Remember, we're looking at a random cards here, but anyway, a packet reversal reverses the cards. Big surprise there. But the reversed order in which you wrote down the cards from the start will now match exactly the ending order of that packet of 8 random cards. Okay, well, that's enough for today. Let me just point out, because it's a very quick calculation, the surprisal value for each and every one of these demonstrations is log base 2 of 8 factorial. Well, that's 15.3 bits of surprisal. And if you remember, the surprisal for being struck by lightning is like 18, technically 18 bits. So it's not far off of the same surprise associated with being struck by lightning. That's how likely it is to have succeeded, okay? And if you remember the coin tossing analogy, which is a powerful way to think about surprisal, is what we have just done. It's the same thing as taking 15 fair coins, tossing them up into the air, while in the air calling heads for all of them. They're all going to land heads up. And then you and the spectator watch as the coins hit the table and bounce and flip and eventually settle down. And all 15 coins are heads up. And you predicted it moments before it happened by chance. Okay, so the surprisal level associated with that random event is the same surprisal level of each of these demonstrations I've just shown you. Okay. Anyway, that's kind of a preview of the Klein 8 group, and it really is just an extension of the Klein Four-Group, where we're using these very important shuffle permutations as the generators. Okay, well, great. Well, thank you, and we'll see you during the next class video.